Hello, everybody. To some of you, good morning. To some of you, good day. To some of you, good evening, and welcome. And thank you for joining us on this webinar on the topic of current transformer testing with iCT1. My name is Andrej Sepcic. I function as a regional area manager in Altanova company, and today I'm going to share with you some knowledge about current transformers and how we test current transformers in Altanova using our latest development, the test set called iCT1. So let us start. So first of all, we'll talk about, of course, current transformer, and let's define the current transformer. A current transformer is an instrument transformer, which means it is not a power transformer. It is not the big beast which is effectively used to transform high voltage onto a low voltage or vice versa. So it's an instrument transformer, and a current transformer is a primary equipment that is used to transform current from high primary value onto a smaller value that can then be used to be sent to secondary equipment like protective relays, energy measurement devices, as an information without damaging them. So these devices are used to tell our energy meters, our power quality meters, also our energy meters, what is the situation on the line, and it does that for different purposes. I will also use this moment to explain one concept. Let me just read this. So let's say the currents on the, let's say, left or high voltage side of the CT are called primary values, while the currents on the right or low voltage side of the CT are called secondary values, referring to the concept of primary and secondary test sets. So a primary test set would be a test set which is generating higher currents and maybe voltages also. That would be a primary, and the secondary would be the one which is generating lower currents and voltages. The primary test set would be the one which imitates currents and voltages which come to the high voltage side of the CT, while a secondary test set will be imitating the currents or voltages coming from the low voltage side of a CT. Here you can see a few types of transformers, current transformers. They can be big, they can be small, depending on the voltage level, and here you can see the symbol for a current transformer. And keep in mind, here you see one line, and here you see two or more turns, and this is to give you some idea on how the CT actually functions. So let us understand how the CT actually functions. In order to do that, let me quote one of famous people in Altanova, Mr. Primo Lodi. He used to say, and he still says it, a transformer does not know what it is. So what did Primo wanted to tell us with that? He wanted us to be aware that in general, a transformer has a primary and a secondary winding, and depending how we connect the source and the output, we can change the functionality of the transformer. So the transformer can be step up or step down, if we put it bluntly. So let's take an example. If we have a 10-to-1 transformer, that means that ideally 10 volts on the primary side will produce 1 volt on the secondary side. But you will see that here I'm talking about voltage, 10 volts on the primary, 1 volt on the secondary. We need to keep in mind that the power on the input is, in ideal case, equal to the power on the output, which means that if I lower my voltage from 10 to 1, I will increase the current. And let us see a little bit more in details how that works. So Primo wanted us to understand that because the power on the input needs to be the same as the power on the output, at the same time, the current on the secondary, if the voltage is 10 times lower, will be 10 times higher than the current on the primary. So let's take this first example, a simple one. We have a transformer which has a ratio 10-to-1. That means that if I have 10 volts on the primary and 1 amp on the primary, on the secondary side, my voltage will be reduced tenfold, so I will have only 1 volt. But in order to keep the power same, I will need to have 10 times higher current. So in this case, we see a transformer, and a current transformer is just the opposite of the one we see above. The current transformer will be something that has more turns on the secondary side than on the primary side, which would make it reduce current and increase voltage. Usually on the primary side, it will have one turn, maybe two, rarely more, but the idea is that, as is in example number 2, you will see that if we have 10 volts and 10 amps, and now we don't have ratio 10 to 1, but 1 to 10, on the secondary side, we will have 100 volts and we will have only 1 amp. So one might say that current transformers are a step-up transformers that effectively increase voltage and reduce current proportionally. Herein lies also one tip and trick which I will share with you. Whenever you use a current transformer, if the primary side is connected, the secondary side should be short-circuited. That's a very important thing to know. If the secondary side is not short-circuited and the primary side is connected and there is current flowing, a high voltage on the secondary side might damage the insulation of your current transformer. So keep in mind, always secondary side short-circuited, and effectively when the current transformer is connected to some protective relay or energy meter, that is already short-circuiting the secondary side because the M meter is effectively a short circuit. So having said that, let us just go quickly, without bothering you too much with certain details, through a vectorial representation of what's happening in the CT when it is operational. Of course, we have the primary side and we have the inductance of the primary side. The IP, or the primary current running through this inductance, creates a flux, and that flux, in turn, using the core, creates the electromagnetic force, which we can see here. Now, this electromagnetic force, in turn, produces a current, and that current is actually the sum of this current and this current. Now, this current here is the losses, and these are the losses for which happen due to the magnetization of the core, and also because we have eddy currents running in the core, and we have to take this into consideration. So that's why, if we look at this graphical representation, this vectorial representation of currents and voltages, we see that if we have the voltage at the ends of the secondary side of a current transformer, that voltage, when you add the voltage drop on the resistance of the winding, gives us the EMF, or electromagnetic force. And then there is the angle phi b, which is the angle between the voltage and the actual current running through the outer circuit or the user or the burden. Of course, that current needs to be, to that current you need to add this current here in order to get the primary current which caused all this. So this is just a short explanation of the, let's say, inner workings of a current transformer. But if we talk about inner workings, let us split one current transformer, look inside and see how the transformer, what transformer actually looks like. So if you were to cut a a current transformer, the things you would see here is that we have primary terminals, and these primary terminals are connected, of course, in series. So current transformer is always connected in series. And then this primary terminal is elongated, is extended onto this, as you can see, this black primary winding. So in this case, we have this winding. And then after this primary winding, we have the core and the secondary winding wrapped around that core. So here you can see also in this case, we have some protection, and often this is inside of some kind of insulating medium, which is either an oil or something like that. Then we have a holder, of course, a porcelain insulator, which holds it in its position. and here we have a graded insulation system, and then in the bottom we'll have the secondary termination box. This is where you would take your copper wires to connect to your energy meters or to connect to your protective relays, and this is just one of many ways how you can construct a current transformer. This is another one. This is another one because here you can see a top cover and an oil indicator, and here you can see oil expansion device. So the oil which is used to insulate this high voltage from the chassis is inside, and the more oil, the higher this goes, and the more, and you will accurately see the amount of oil inside. Then in this particular design, the low voltage or the secondary side is placed here, and then here we have the actual connection to the outside grid, to the primary side. So as you can see, it's in series. And then we have some insulation here. We have a porcelain insulator. Of course, it can also be silicon on the outside. And here we have a high voltage bushing with intermediate screens. And long story short, here we have a base and the box where you connect your secondary side. So this is another design. And if we go to a substation, we will see something which looks like this. For example, this is a picture of a CT in a substation. And here is a picture of a CT which was produced in a factory. And we can see right away that this is a top cover which holds the insulation inside. We have oil level indicators which cannot be seen right here due to the perception. And the important thing is that number 5, this is the primary side. This is where you connect, and you can see that here we have connected line in series. After that, we have a porcelain insulator which holds everything in place. It can also be, as we said, the silicon insulator, and then we have the termination box where you connect your instruments, and the base to which the CT is connected. So this is what you would see, and you can recognize right away when you see a CT in a substation just by how it is connected and the position of a CT. Talking about some other types of CT, or let's say in general, trying to explain what types of CTs exist, we can say that we have a bar primary type, which are the ones we more or less saw, and this one is used for currents greater than 100 amps more or less. And we have a wound primary type, which is used for smaller currents due to thermal and structural limitations. Today, we need to also discern one thing. When we are talking about current transformers, we need to distinguish between metering CT and the protective CT. So what would be the major difference between these two? Well, the major difference would definitely be the knee voltage, and the part from the knee voltage, it will be accuracy. The knee voltage, and we will see that later for protective CT, is much higher than the knee voltage for metering CTs, and we will see why, while accuracy for metering CT is much higher than the accuracy for protection CT. Why is that? Well, it is because if you're using a metering CT, you have to know as accurately as possible how much current is running in the primary side in order to be able to measure that and charge your client with an accurate value. How much energy did he or she consume? On the other side, the protective CT does not care about 1 or 2 or 3% of error, simply because when you have a fault and CTs, protective CTs, are here to protect you from the fault, in that case, you have actually, you have to be very fast, but you don't have to be very accurate. So simply because when you have a fault, as we said, on the line, then your current is not increased 1, 2, 3, or 5%. It's increased 1, 2, 3, or 500%, and that's why accuracy is, let's say, secondary when we talk about a protective CT. But let us go a little bit more in depth. So metering CTs are very accurate, up to 100 or up to 150% of full load current. Above that values, metering CTs need to saturate in order to protect the inputs of the instruments under fault conditions. Why is that? Well, it's because, first of all, metering devices have very sensitive inputs due to the high accuracy. And if you stress them too much, they might burn. So a CT, metering CT, is put in place, is designed in a way that if you have a fault, it will not be transformed accurately on the secondary side, A, to protect the inputs of metering devices, and also B, because maybe you don't want to charge the fault current which is happening for these few hundreds of milliseconds, because effectively your customer is not using that current. So this is why metering CTs have to saturate under fault conditions. And because they need to saturate after fault, in fault conditions, they often have a very sharp magnetization characteristics. And the knee point voltage is usually few volts to few tens of volts, depending on the application. On the other side, protection CTs need to accurately transform a wide range of currents, from nominal or less to maximum fault currents, which can be 10, 20, or even 30 times your nominal current. So saturation should be avoided at all costs in order to accurately transform primary to a secondary current, and the trade-off, unfortunately, is accuracy compared to metering CTs. But as we said before, for protection CTs, accuracy is not that important. In that case, knee point is usually found at few hundreds, sometimes it may be a little less, and sometimes even few kilovolts. So sometimes I would like to do one comparison, let's say, of metering and protection CTs. I don't know if you guys saw Mad Max in the 80s. You might remember in one sequel of Mad Max, there was Master Blaster. You had this huge guy who was carrying a very small, let's say, short person on its backs, who was the brains, and the big guy below was the brawn, was the power. And here you can say that the metering CT is the brains, while the protection CT is the power below. And why is that? Well, it's because, let's say that if you have a distance protection which is fed from one current transformer, and there is a short circuit, a line breaks and touches the ground, your distance protection needs to know accurately what is the current, because according to that current it will calculate the impedance, and according to that impedance it will calculate the zone, and according to the zone it will know when it should trip. If it doesn't calculate that correctly, it might miss opening the circuit breaker, or it might open a circuit breaker when it shouldn't, which is effectively a problem. So for your CT, which can be, let's say, 2000 to 1, and if you have a fault and your current is 5-fold, it's 10,000, 10 kiloamps, the protective CT should say on the secondary side exactly how much the current on the primary side is, in order to give correct information to the protective relays, while at the same time metering CT will saturate and will not burn the inputs of metering devices which measure the energy which was given to the user. So I hope I'm making myself clear, but in order to completely explain what is the knee point, we will show you this, which says the knee point is defined as the voltage at which a 10% increase in applied voltage increase the magnetizing current by 50%. So for voltages greater than the knee point, the magnetizing current increases considerably, even for small increments in voltages across the secondary terminals. And this effectively means that when you reach your knee point, and if you increase the current on the primary side, on the secondary side, nothing will increase. You will stay in the same position, you will have the same current, which will then not provide a correct information if we talk about protective CTs, and which will then protect the metering devices if we talk about metering CTs. And since we also spoke about a sharp magnetization curves, we can see that for a metering CT, you will have something like that as your magnetization curve, while a magnetization curve for a protection CT will look something like this. And at the same time, let's say the knee point is here, this will be 10, 20, 30, 50, something like that. Not more than 100, probably. Maybe in some cases there will be, because there are many types of CTs. While in this case, if we have the knee point here, this will be 100 or 300 or 400 or 1 kilovolt or 2 kilovolt. I'm emphasizing this concept of the knee point because we will see later that one of the tests is intended to measure this knee point, and also because we said that the knee point is the prime differentiator when it comes to differentiating between metering CTs or measurement CTs and the protective CTs. Also, moving on, we will see that we will talk about two aspects. One of them is called ALF, the other one is called ISF, and the ALF is something which describes the behavior of a protective CT. ALF is a short for accuracy limit factor, and in order to maintain the accuracy of a CT during the fault, our device needs to correctly transform the primary side values onto the secondary side. So point being, protective CTs should not saturate even under high fault currents, as we said before, 10, 20, or 30 times more than nominal, excuse me. So I think the best way to explain ALF are these two examples. When you look at the protective CT, you will always see some kind of marking like this, 5P10 or 10P30. There are few combinations. The P here stands for protection, and then let's see, and in this case, number 10 is ALF. Number 10 is ALF. Here is ALF 10. Here we have ALF 30. So what does this mean? This means that if my primary current is 10 times bigger than the nominal current, in that mode of operation, the error on this CT, the accuracy, shouldn't be worse than 5%. So 5P10 means that if you have 10 times nominal current, the accuracy should be not less than 5% at 10 times nominal current. On the other side, if we have 10P30, this is something more robust. In this case, if we go 30 times more than your nominal current, the error at 30 times nominal current cannot be more than 10%. So if we have 1000 to 1 CT, and if there is a fault, and there is 30 times nominal current running in the primary side, so it's 30 kiloamps running in the primary side, on the secondary side, you will have to have 30 amps. That would be ideal, but if you have 30.3, which is still good, 30.4 would not be good. So this is ALF, and ALF is reserved for the explanation how the protective CT works. Metering CT, on the other side, uses a number called ISF, instrument safety factor. So metering CTs have to protect sensitive inputs of energy meters, and they are connected to. That is why they need to saturate soon after 100% of nominal current in the primary side when it's reached. So ratio of instrument limit primary current or saturation current to the ratio of primary current. Let's say the instrument will limit the primary current of metering CT beyond the value of the primary current, which is here explained. So long story short, how high will your primary current go until the secondary current stops growing? So if I have ISF 5, that means that CT will saturate when the primary current is 5 times nominal current. So this is ISF. ALF, protective CTs, ISF, something else. So these are the basics of current transformers I wanted to share with you. Now let us move on and let us see how iCT1 handles those CTs, how it measures those parameters. And iCT1 is fully automatic current and voltage transformer test set with integrated switch box. That's something you can already see on this picture, but before we explain what is this device made of, let us say that this device is designed to test current, voltage, and combined transformers. Time-saving testing means that with integrated switch box, you can set up only once, connect all the outputs of the secondary side, and do a test all at once. The main tests that this device performs is ratio and phase error, excitation curve or the knee point voltage, resistance, which is winding resistance, accuracy, burden, etc. This device has integrated 5 taps switch box, and it is able to test CTs, and this is important, with saturation voltage up to 2 kilovolts using 50 Hertz signal. So iCT1 inside carries a transformer which can generate up to 2 kilovolts in 50 Hertz. And 50 Hertz, it's important to emphasize because this is necessary to test according to standards all current transformers. Now, here we also see and up to 30 kV, but then we have a note applying DC indirect method. If you have a huge current transformer with a knee point of 6 kilovolts, it would be difficult to test the knee voltage using the standard method. In that case, we use a different method, so-called indirect method, applying DC voltage, and we will talk about that later. iCT1 also carries an integrated demagnetizer inside. Demagnetizing is very important every once in a while because you can have a CT working all the time at the limits of its saturation and you wouldn't know that. But as soon as the fault comes, you would have wrong readings on the secondary side. So it's a good practice every few years maybe to demagnetize your current transformers to be sure what is their working point. We also have something very cute and interesting inside of this device. It is called a CT Explorer. So if you have an CT without any nameplate, using this function, in a matter of 2 to 3 minutes, you will find all necessary data on your current transformer. Nominal current, ratio, burden, etc., etc. And it's important to emphasize that this is also compact and lightweight device. So it has about 16 kilos, and you can see here the dimensions: 410 millimeters in height, 340 millimeters in width, and 205 millimeters in depth. Now, to look at the device, let's see what is it made of. First of all, we have a Wi-Fi communication with the computer. This is only one of the ways. Of course, you can also use Ethernet, but since it's something which we think is good to use when you are testing sometimes in an environment with high voltages, Wi-Fi is the mean of communication with your PC if you are controlling the device from PC. But of course, you don't need to control it from the PC. You would be suggested to use the touch screen, 7-inch touch screen display. So all is done just with your fingers. Of course, here is the 6 terminals integrated switch box. Is it 5 or 6? We will see later. Actually, you have 6 connections, but you can test a CT with 5 taps. And we also have here, as mentioned before, Ethernet and USB port. So USB port is used not to connect the PC, but to connect your USB stick or pen drive, as some call it, in order to save some data or to transfer them to iCT1. And Ethernet is used to connect also with PC, and everything is put in a rugged case with a handle. So this is the description of the instrument, which is the latest product from our R&D team. And this instrument, as mentioned before, is one device which is used to test current transformers, voltage transformers, and combined transformers. Now, here are all the functions listed, which can be tested using iCT1. For a CT, we can do turn and ratio in polarity mode. We can test the burden, secondary side, excitation curve using a standard method up to 2 kilovolts, and we can also do excitation curve in DC method. Winding or burden resistance can be tested, and as mentioned before, ALF and ISF, accuracy limiting factor and instrument safety factor. No load current, AC, accuracy test can be performed. There is a demagnetizer or CT Wizard or CT Explorer, as we call it. What you can see here is that we have two models, advanced and standard. And the biggest differentiator is the excitation curve using the DC method. So the advanced option will also have the possibility to test your CTs, which have the knee point above 2 kilovolts, while the standard one will have the option to test up to only 2 kilovolts using 50 Hertz signal. And of course, since it is the latest product when it comes to this type of testing equipment, we follow all older, which is 644 standards, and newer 61869 standard from IC. We also comply with IEEE C57.13.1. So this is important to mention. We do test according to standards using the devices, using the signals which are prescribed in standards. And even though today we're talking about CTs, because iCT1 can also test VTs, let me just list the number of tests you can do on a voltage transformer. You can test ratio, you can test ratio of electronic voltage transformers, you can test no load current, and the latest development is also the ability to test accuracy on VTs. So just to close this part and to explain what is the biggest difference between standard and advanced version of iCT1, the standard version does not have, an advanced version does have excitation curve using DC method. Why is this needed? So it is needed for CTs that have the knee point above 2 kilovolts. And in practice, this is not written in stone, but more or less you might say that the CTs which are used for voltage levels of 220, 230, or 400 kilovolts and above, these installations have the tendency to have CTs with the knee point which is higher than 2 kilovolts. What are the outputs of this device? So output characteristics. We have one main generator that has 5 outputs. High AC voltage, which is used to test for the knee point, for magnetization curve. Low AC current, low DC current. Low DC current would be used, for example, for winding resistance. Low AC voltage and low voltage for excitation curve DC method. Let's see some of the characteristics. High AC voltage can go as high as 2 kilovolts, and at 1 amp we can go for a few seconds. With a lower amperage we can go for more than 120 seconds, and maximum current you can get from this source is 15 amps, and this is at 9 volts. Low DC current, which is used, as we said, to test our winding resistance, is maximum 6 amps, and it's important to say that this is pure DC, and it's amazing how quickly we can get the results of winding resistance. We have other devices in our portfolio of test sets, but this is the one which measures the resistance the fastest, by far. We, as mentioned before, low AC current. It also goes as high as 6 amps with a maximum power of 200 volt amps and 100 volts. There is a low DC voltage for excitation up to 30 kilovolts. So in that case, the absolute maximum is 200 volts DC, and the maximum output current is 2 amps RMS. And at that time, the maximum power is 400 VAs for 230 volt supply and 330 VAs for 110 volts supply. All of these outputs, not all of them, but the ones who are in alternate, can give us the frequency from 15 to 400 hertz with a resolution of 10 millihertz, and all the outputs are electronically protected, which is very important. Now, another thing which is important to be emphasized is the very, very accurate measurement of iCT1. So this instrument performs simultaneously the measures of voltages on the primary and the secondary side. For example, when we do ratio test, what we actually do is we generate voltage on the secondary side and we measure the voltage on the primary side. That's important. You will see that in the video. You can see that the accuracy, you can see that the typical errors here are very small, 0.02. Well, let me be blunt. The guaranteed are somewhat bigger, but still it's 0.05. So with this, you are free to test more or less all types of your current and voltage transformers, whether they are protective or they are metering CTs. Now, when we do combined measurement like ratio, we need to generate and we need to measure. And again, we have a typical accuracy of 0.02 up to 0.05, depending on the range ratio. And there is a maximum accuracy, which is between 0.05 and 0.2. Again, I would say most of the CTs lie in this region, maybe this region. Of course, if you have a CT something to 1, then definitely it might also touch this region. But if you have something to 5, then probably you will be in this region here. So very high accuracy on the ratio. Also, when we talk about VT, it's the same story. Between, in this case, 0.03 and 0.05 would be our typical accuracy, and guaranteed accuracy will be between 0.2 and 0.5. Burden test measurement. So for burden test, the result is a product of voltage and current. The accuracy depends upon the VA range. So the following table, as you can see here, lists the parameters for the burden test. In this case, we are using the AC voltage in different ranges. Also, there is a current correlated with that, and there is a special, of course, at the same time, there is the power. So what you can see is usually your CTs will be in the range of about 10, 20, 30, 40 VAs. Rarely will you go as high as this, but I'm not saying that they don't exist. So the resolution is also very high, and the accuracy you can see here is between 0.1 and 0.2%, which is again very high accuracy. Winding resistance, whoever did test CT until now, they understand that the winding resistance can be, well, let me say the longest test. It's not very long, it's sometimes half a minute, sometimes a minute, but in this case, it's much faster. We use 6 amps with a resolution of here, as we can say, 0.1 milliohm. So 0.1 milliohm is the resolution, and the typical accuracy is 0.05%, while the guaranteed accuracy is 0.1%. This is very, very accurate, and trust me, it's very fast. You will see it in the upcoming movie, which I will show. And let us close this section about accuracy, phase angle measurement. So, of course, there are 2 values. In AC, they need to be measured, the angle between them needs to be measured. So, of course, the metering range is between 0 and 360 degrees with a resolution of 0.01 degree. And accuracy is typical less than 2 minutes and guaranteed 4 minutes. So this is really very, very high accuracy. So let us say that this device can be applied in factories and for commissioning because it is very accurate, it's fast, it's multifunctional, it is easy for transportation, and it abides to all international standards using the 50 Hz method, apart from the situation where we need to go more than 2 kilovolts.